This is Section 4 of Unit 3, Loan Calculations and Regression. Our quote for this lesson is, "Loans and debts make worriers and frets." It's a traditional proverb. So let's see how loans make worries. The objectives are to determine the interest on a loan given the principal, time, and APR, to use logarithmic loan length formula to determine the term of a loan, and to use regression to find the curve of best fit using data from a loan table. We have a few key terms here. We have monthly payment calculator. This is an online tool used to calculate information about the balance over the lifetime of the loan. There's the loan length formula, a formula that uses both algebraic and logarithmic properties to solve for time. There's cubic function, a function containing an exponent whose highest value is 3. This is also referred to as degree 3. And then lastly, cubic regression equation, a third-degree regression equation of the form y equals ax cubed plus bx squared plus cx plus d. We're going to find that this cubic regression equation is most often used when it comes to loans and finding the best fit. It's a better fit than either linear or quadratic. So let's look at a table. So to figure out how can you calculate and model loan computations. So let's say that we're borrowing $100,000. The interest rate is 7.5%. The term is 15 years, and the start date is January 2010. All right? Now, this shows basically how the monthly payments are divided up. You can calculate your monthly payment. The monthly payment is $927.01. So this is the amount every month that's going to be paid. However, obviously, the portion of that's principal and the portion of that that's interest is going to change. For example, notice, starting off in January 2010, the principal is $302, the interest is $625. Let's move down to November. The principal is $321, the interest is now $605, okay? So you can see that the interest each month is going down, while the principal being paid back is going up, and that's in order to maintain this constant monthly payment of $927.01. So let's look at our first example. Determine the total interest owed on a 5-year, $10,000 loan at 6% APR. All right, so we're going to use the monthly payment formula that we learned before. Our principal is $10,000. Our interest rate is 0.06. Remember, we do it as a decimal, and the time is 5 years. So we plug it into our formula here. P, R, and T are the unknowns, which we already figured out. And we come out with a monthly payment of $193.33. Now, it's a 5-year loan. That means there's 60 months. So we multiply the monthly payment times 60 months, and we come out with a grand total of $11,599.80, which is paid back. But the original loan was only $10,000, all right? So if we subtract these two, we come out with the total interest that's paid on this loan, $1,599.80. So let's look at another example. Claude wants to borrow $25,000 to purchase a car. After looking at his monthly budget, he realizes that all he can afford to pay per month is $300. The bank is offering a 5.9% loan. What would need to be the length of his loan so that he can stay within his budget? All right, so what we're going to do is we're going to take the previous monthly payment formula and solve it for t, for the time, okay? And that gives us this rather ugly looking formula, which involves logs. Now, we know the principal is $25,000. We know his monthly payment that he wants is $300. And we know the interest is 0.059 or 5.9%. So if I plug all these values in and use our calculator, we come out with 8.96 years. Well, obviously we can't talk about a portion of a year, so basically the length of his loan would have to be 9 years in order to have a monthly payment of $300. So here's another example. John does not have a very good credit rating. In January of 2016, he found a lending institution that was willing to loan him $100,000 for 15 years at a higher than normal interest rate of 7.5% because of his poor credit rating. Looks like he might be purchasing a small house or something like that, or maybe land. Examine the table of decreasing loan balances over the 15-year period. Use regression to determine a curve of best fit for this data. So as you can see, we have a table on the left side here showing the different years, okay, and the end of year loan balance for each of these 15 years. So starting out, his $100,000 after the end of the first year, he's down to 96, and then all the way down to 0, all right? Now, if we plot these, we would get a graph that looks something like this right here. And if we look for regression to determine a curve of best fit, you'll recall that I said earlier that when it comes to finances and loans, the curve of best fit tends to be a cubic, okay? So if we used our graphing calculators or Desmos, we would come out with this for our line of best fit. And as you can see, this, if I graph this curve, it almost follows exactly those points. All right, so now we want to plug in x equals 2 into the regression formula and see how it compares with the loan balance on the chart for 2017. Okay, because let's see if this formula is really as accurate as we think it is. So if I plug in x equals 2 into my formula, this is what I come up with. I come up with $92,190.50. Well, if I look at year 2 on the table, it's $92,206.05. So these are fairly close together, okay? So it looks like our regression formula is pretty accurate.